what are these slides and where are they getting all these colors that are the stains on the slide? And someone shared to explain to me, oh, these are coming from biopsies, and the biopsies are then going through chemical processes, and these things are basically highlighting features in the tissues, and then pathologists can actually look at them and make diagnosis. So I asked, okay, if we learn how to extract better, higher resolution from a slide, why can't we teach a model to just do this type of staining? And that was really the genesis of Pictor.
Welcome to the People of Pathology podcast. I'm Dennis Strank. On this podcast, we explore pathology one story at a time and connect with the people behind the diagnosis. Slide staining in pathology is often an automated process these days, but the actual chemical stains haven't really changed much in about a century. Today, we'll look at an exciting new technology in pathology, virtual staining. My guest is Yair Rivenson, CEO and co-founder of Pictor Labs. We'll talk about the origin of Pictor Labs and how this technology was developed. Then we'll get into the advantages of virtual staining. All right, let's get started with Yair Rivenson. Let's get some context and you a little bit of background information. So I know you started your career in engineering and academic research. So let's start there. Like, what drew you to engineering in the first place?
Yeah, so I have to admit, I've always been fascinated by understanding of natural phenomena. So mathematics and physics, and at some point very early on, computer science. Actually, I went through the route of gaming and then trying to understand how the games work. I went to more of the computer science side. And actually, that's part of what drew me there, trying to understand how things really work and understand their hidden aspects, whether if it's a natural world or, anything else such as a man-made phenomenon, trying to really understand what causes that and things that are not always obvious to the naked eye. And at the end, this brought me to work on, first of all, signal processing, a lot of signal processing, and then image processing, and then what is now called computational imaging, and then focusing on biomedical imaging, where they can combine both light and biology and computation. That intersection, I feel like, was where I really found my niche.
How did it come to biomedical imaging? Like, how did that start, I guess? Because that's really where we're going to go with this conversation. So what was the beginning of that?
Yeah, biomedical imaging was really, I only started touching on that at post-graduation, at the postdoc that I came here to UCLA. So during my PhD and master studies, I was really focusing on computer vision algorithms, but it was very theoretical in a sense. So I derived all these really cool equations, very
Mhm.
proud of. But what I really wanted to do in my postdoc is, okay, so now I think I truly have the grasp of this. I want to apply it to real problems. Biomedical imaging and specifically microscopy is where I thought I would get the best benefit from what I did back in my graduate studies.
Can you take me through the origin of the project that eventually became Pictor Labs? Like, I kind of want to get to this whole, you've told me parts of this story, but I kind of want to get the whole thing. So how did this start?
Yeah, absolutely. I'll go again, early days when I started the postdoc here in UCLA. We work on, again, applying what I did, like graduate studies, to more of the biomedical world and the research theme of the lab. And, we were doing really well, published a few papers. And then deep learning started to make some noise at that time. At the beginning, deep learning, comes out as the best type of classification of results that there are for computer vision. That's where it breaks out. It's like coming out party, if you would. And people try to take this into microscopy and classify cells and things of that nature. I was more interested in how can we take this and increase the details that you can extract from each and every microscopy image, which is exactly aligned with what I did in my graduate studies. So I think
Mhm.
that's what drew me to that. At that time, you have some papers starting to come out that talks about what is called super resolution. So that seemed to us like a perfect settings for this type deep network learning. Anyways, long story short, I'll get to I'm getting to the Pictor part.
Okay.
And what happened was we started publishing these works. They got a lot of skepticism. And I think we were really at some point thinking, okay, this is really interesting. People are just super resolution and those type of things are too much. At some point we got it through. And once we got it through, we were like sitting in a lab and we're thinking, okay, that was not easy, but like we really believed in what we were doing. And we're asking what's next. And we had literally pathology slides laying around in the lab. And again, my background, again, as everyone understands right by now, and then it's engineering. And I asked the very naive question, what are these slides and where are they getting all these colors that are the stains on the slide? And someone cared to explain to me, oh, these are coming from biopsies, and the biopsies are then going through chemical processes, and these things are basically highlighting features in the tissues, and then pathologists can actually look at them and make diagnosis. So I asked, okay, if we learn how to extract better, higher resolution from a slide, why can't we teach a model to just do this type of staining? And that was really the genesis of Pictor. In like a couple of months, we put together all the measurements and trained the networks to show this thing works. And since then, we didn't look any other way, just forward.
Okay. That's an interesting story because I've noticed, I've been in this field for a little while, and I've noticed that some of the greatest advances in technology come from outside of the field. Somebody looks at it with a different point of view than a pathologist or someone who works in pathology, which is what you did. You're looking at it from the outside and going, why can't we do this? It's something that probably no one has ever thought of before.
Yeah, thank you. I mean, it's one of those things is thinking about something, as you said, having the conviction that it could work, try it
Uh-huh.
out, and when you see it work, just grabbing that and not letting go. I think that's again my moral of this story.
Yeah. So you found that you could do this. This technology worked. How did you determine there was a need for it?
Wow. So that's another interesting story. There was this pathologist who we were working on. I'll keep him nameless for the sake of this call. I went to meet with him. I was then kind of talking to him about pathology and super resolution. He was kind of lukewarm on that. Like, okay, fine, I'll just image with a higher magnification or something. Anyways, and then I'm like, hey, oh, by the way, I have this thing. So here's an unstained tissue section. And I do these triplets on the slide. You have the unstained tissue section, you have the virtually stained tissue section, and you have the ground truth, which is produced by chemistry. And I start showing him those triplets, and the guy kind of losing his breath.
Oh,
And at that point, I was like, okay, might be onto something here. But really, after that anecdote, which just, I think, made me, okay, I need to learn what is really interesting and what happened here. It is some sort of a learning curve for me, as you probably can figure, because of my non-pathology background. And for
right.
me, pathology is it's a such an interesting discipline, and I, gather like probably most medical sciences, it's built on experience and art of pattern recognition, and multiple years of experience. I spend a lot of time around pathologists trying to understand what they're interested with this technology. Some of those sitting in a microscope, going to one of those OR suites, spending time at Mohs surgery, where again, everyone's so gracious of letting me in and seeing how those things are actually working and what's their pain points and how they run the process. And, it became clear that the current staining process, this is, again, the most fundamental process in histology, is also creating some level of a bottleneck. I could see that it was slow, that because I was using those things myself to train the algorithm. So I could start seeing that it's not as fast as it should be. I could start seeing variation between labs. And then one of the things that I've learned very quickly is about how much it consumes the precious tissues. As I was starting to talk more and more pathologists, especially ones that are in the industry. And that's how we understood that we need to develop this IP into an AI driven equivalent.
So then you founded Pictor. Actually, I'm curious about the name Pictor. Does that have a meaning? Does it have a story behind it? What does that mean?
Yeah. My co-founder, Professor Oskin, came up with the name. And Pictor means painter in Latin. It's also a constellation in the sky, I believe in sovereign sky.
Okay.
And it represents the easel of an artist. And to us, it felt fitting because our technology is about painting images. Our images is slides, and we do it with machine learning and data science instead of a paintbrush. But that's where the name came from.
That's an interesting story. Now, Pictor, I think, was founded in what, 2020? Did I read that correctly?
We formed in 2019, but we
2019.
actually got off the ground to any activity at the end of 2020.
Okay, I see. So let's kind of get an overview of what Pictor Labs does. So you're replacing chemical staining, like you mentioned, with AI-powered virtual staining. Can you kind of explain for us? I know this is an audio-only format, so this might be difficult, but how does this work? As much as you can tell us anyways, from kind of acquiring the image to what the final virtual stain looks like.
Yeah, absolutely. The gist of it is that, in traditional pathology, we perform this chemical processes, which we call staining, to reveal or highlight the tissue structures. What we do in Pictor is basically using light tissue interaction, and then on top of it, machine learning process to predict how this thing looks like. So when we started our path, and today also, we have started with what we call an autofluorescence. Autofluorescence is a result of natural light emitted by tissue when excited with certain wavelengths. So that's our input signal. Then we image the tissue with that autofluorescence, and then we take the same tissue and we perform the standard staining process. Now, at that point, what we do is a very careful alignment of the autofluorescence image and the stained tissue image, and pixel by pixel. And at that point, we basically learn the transformation or the translation between the autofluorescence image of the tissue and the stained version of the tissue. We do it in a supervised learning manner because, again, they're coming from the same material. In other words, every pixel on the autofluorescence image is accounted for with the stained image. Once we have trained the model, again, in this supervised learning fashion, we can then take the model and run new slides through it. And we right now serve it through cloud service, if you would. We can do it also on-prem. But really the cool thing is once the model is being trained and you don't need too many slides to train the model, you can probably, we get very good results after around anywhere between 80 to 120 slides. Again, depends on the size of the slides, because again, we're trying to learn sort of a very minute pixel, sub-pixel level translation. So that's how the algorithm learn. You know, what's really amazing about machine learning algorithms is that they're just doing compression. So if you think about our algorithm, I could take a model that we created and put it on a thumb drive. And these thumb drives are equivalent to some extent to a whole lab. And that's, I think, the beauty of it. And again, the same thing is I could say about large language models and vision language models. But really think about it. You take like the chemistry part of the lab and you compress it to something that is a thumb drive size. And that's just incredible.
This is the People of Pathology podcast with our guest, Yair Rivenson. We'll be right back. When it comes to cancer staging, one of the most important parts is finding all of the lymph nodes. I should know, it's what I do every day. Yet this process has remained the same for over 100 years, manual, tedious, and time-consuming. That's a problem because every missed lymph node can mean inaccurate cancer staging. That's about to change. Enter InVision from Cision Vision, a first-of-its-kind device that's redefining the standard of care. Traditionally, we identify lymph nodes by sight and feel alone. InVision changes that using short-wave infrared technology to make lymph nodes stand out clearly from surrounding fat and in real time. In its first 104-patient study published in the Journal of Clinical Pathology, InVision helped increase lymph node counts in 86% of cases and even upstage 4% of patients from N0 to N1. I personally contributed to the study, and let me tell you, seeing the technology's impact firsthand was amazing. It's time to invest in grossing innovations that improve patient care. So, how is your lab approaching innovation in grossing? Book a demo at demo.cisionvision.com and start seeing lymph nodes like never before. Are you thinking about applying to a pathologist assistance program and feeling a little lost? That's why I created the Path to PathA, your PA school application blueprint. This is a step-by-step prep course that gives you everything you need for a strong application. From finding shadowing to writing a standout personal statement to prepping for interviews, this course was made to help you feel informed, confident, and ready. Visit www.thepathtopatha.com to join the mailing list. You'll be the first to hear when the course launches. Your path starts here. Now for the rest of my conversation with Yair Rivenson on the People of Pathology podcast. So I know you have you've got the standard H&E stain, you've got a lot of immunohistochemistry stains, some of the special stains. What does it take to train a model to bring on a new stain? And how long does it typically take to do something like that?
Right. So I will kind of continue from where I was.
Okay.
The way, again, we need to be between 80, 120 to 120 slides. Train a model, again, depends on the model, on the another model size. The slide, like what, if we're getting a lot of biopsy, there are resections, and you have more data to train from a resection versus a biopsy, for example, versus, I don't know, maybe a TMA. So everything needs to be taken into account. But once we created this data set, and we aligned it and we ran the supervised training, what we do is we go with these models and we demonstrate to the partners we're working with. And in many cases, we're often being told, hey, this is awesome and would like to work with these. And then we would like also to develop the following, especially with the pharma partners that we have. That's kind of where the things are going. We kind of coming up with our own ideas for what types of stains we're developing based on what we know are the clinical needs and the volumes. But really, we're primarily geared to our customers, where we see right now the most value for this type of technology.
Is there like a typical time frame for developing a new stain?
Yeah. So we worked on the automation of this in the last year, and we have an internal code name for that, Dash. And what we do in this project is really all about automating those workflows of creating a new slide. I think the biggest bottlenecks we see is getting the data. Once you have the data, though, it really can take 3 to 5 weeks to get a model ready to be shipped. That's it. I mean, because it's most of it, the process is automatic right now. And you then become dependent on compute and pathologist review of the model. And that
Okay.
those are, but really always the bottleneck. And I think it's always for the same thing for every machine learning or AI company. What you see is, the standard things, which is compute and data. Those are always the bottlenecks.
Okay. Still, at 3 to 5 weeks, that doesn't sound like very long to create a new stain.
It's not. We are tuning our models in many cases now, so it makes it even faster sometimes. We can get, I think our record is around 10 days.
Wow.
Yeah, that was something else. But again, it's not just obviously, I'm talking about technology and automation, but really it's a lot about the team as well.
Hmm.
We have some experienced engineers on the team that have done it. And it's, if you wake them up in the middle of the night, tell them I need to build a model, they'll, sure. Like they're like, we'll build you the best possible models very quickly. So it's also about that, the team and the people, with some group of very special people here around.
So you mentioned the pharma companies you're kind of partnered with. And I'm curious, when it comes to developing new stains and how you decide which new ones you're going to bring on, is that partially from the pharma companies? Like we'd like to see these stains. Are there other influences like that?
Yeah. So we're trying to find these biomarkers that will intersect between what's being ordered a lot in the clinical world versus, what we're hearing in discussions with pharma. Pharma in many cases wants something even different than all of these that we always come like, you know what? I really want something, and like, yeah, well, we haven't heard of that one, but sure.
Okay.
I think that kind of drives a lot of the development cycles. But I mean, what's really important is that we are taking our menu and keep on expanding it to more and more indications. And with this underlying data engine, it just becomes, again, the concern is just, hey, how do I get the data? Then I just throw it to the data engine and it crunches it and creates the model from there. So again, it's mostly this is a decision that is coming in by what the fund partners request. As you can probably figure out, it's like a lot of more immune type of markers that they're looking at, which is again very interesting. Less used in the clinical world, but we're looking for some other targets in the pharma world.
There's one thing about this technology that I really want to highlight because we're in a world where biopsies are small and the number of tests that are now required on those keeps getting higher and higher. I mean, we're talking about the regular, H&E stains plus the IHC stains, plus we're talking about molecular testing, all this stuff. The thing about your technology that is relevant here is that in theory, you can do an infinite number of stains on a single piece of tissue because you're not using any tissue to do the stains, right? I mean, was this part of the initial idea at the beginning to be able to kind of do more with less?
Yeah, I mean, it was kind of from the beginning. I believe it's on the first paper we are talking about that. We realized very early that this would be an advantage of this technology. Again, just by interacting with pathologists in the pathology lab in UCLA and asking them questions, and you start understanding that this is a problem. What I didn't appreciate back then was how much of a problem it was. And you meet people at all sorts of walks of life, and you tell them what you do, and then all of a sudden people start telling you, hey, I know someone from my life that had to go and do rebiopsy because it was not enough material to work with.
Yeah.
And you hear more and more of these stories. At the beginning, we understood it from an engineering perspective, but then you start understanding, where it actually meets people on their daily lives and what type of a change this could bring. Because again, this is for patients. Same thing I could say for pharma. And if we could help streamline some of the time that is required for the clinical studies, because you don't need to run through the blocks that you buy, you just run it all virtually, and
Mhm.
then you could go and put it on saying, okay, here's what this block has, here's what this block doesn't have, which drug programs does it fit. And all of a sudden you get a completely different view of how you can use a tissue block, because again, you create some sort of and it's very fashionable to say digital twin of the block. And that
Right.
digital twin is really becoming that asset that you can run all these different hypotheses, and it's all in silico. So again, you just don't run through it. And once you understand what is the best fit, what's the best hypothesis, you can just run with it. Yeah, this is one of the most interesting value proposition, again, from patient perspective and from biopharma perspective.
Yeah. Yeah, for sure. Something you mentioned before, I think it was the last time we talked, you said that this technology can become a data layer for pathology. Can you explain, what did you mean by that?
Yeah, so I think of pathology slides right now are kind of some sort of a visual artifact. You look at them, interpret them, and that's it. Okay, we're done in some senses. Hopefully, we're done. By the way, like when
Mm,
someone has to review it, it's not always a good thing. What I get, but that's kind of where it is. I'm thinking that this technology is making slides into like a computable data, like some sort of a living, if you would, living data set that you can basically, again, run hypothesis at different time and different places in order to reveal more things that you might have not have the ability to reveal before. You can start correlating morphologies that didn't have contrast. You can start doing all sorts of correlation with molecular data. You can start linking histology maybe more directly to outcomes just because you can run all these different tests on the same tissue section. Which again, those technologies, at least some of those that I just mentioned, are already exist. The problem is they're not very scalable and are susceptible to, what all the good things we talked about before. It's the
right.
destroying the tissue and making some of the staining is non-repeatable or there's variation. So in a sense, this virtual staining is not just replacing the lab process. I think it's creating a foundation for some sort of a new digital pathology ecosystem. And it kind of unlocks that more of a meaning out of each and every specimen. And once we have those more and more of these stains available and everything's aligned, I would like to see how people are, Pictor as well, but other players will take this forward to, again, a new type of science and applications that could be done from these data sets.
All right. So then looking ahead, what's next for Pictor Labs as far as like expanding the technology or maybe it having more of an impact on like clinical workflows, things like that?
Yeah, you sort of hit it. Obviously, we keep on expanding our virtual staining portfolio across tissue types and stains. We just want to bring, the power of these models to more applications in pharma CRO, and eventually, as you mentioned, I think the bigger one, and I think that's what we all sign up for, is the clinical workflows. We want to make a very positive impact for labs that will one day work with this technology, hopefully, with clinical type of data. Where are you all right now, completely, just to kind of put it the right disclaimer. So that's where everyone wants this technology, I think, to go to. What's really interesting for us is integrating into the current pathology pipelines, which is a nice way of saying we want to be integrated with hardware image management systems, LIS systems, in order to really get this technology available and just really create a very wide type of distribution. Because again, think about it. It's the best possible distribution type of mechanism. Now we have these models available. Take them for a ride, as they say. And I think that's hopefully where we'll go with this. And it's so much different than current state of affairs where like you need to order reagents
Right.
and optimize, discard the chemical waste and all the good things. Again, so all these things will hopefully be a thing of the past, or at least most of them to an extent, when this technology is just becoming more abundant.
Hmm. I mean, you hit upon a really interesting point right there, as far as there's no chemical waste, which we have now. We talked about less tissue required. There's a reduction in time. A lot of I think just the waste aspect might be a good enough reason to really look at this technology and, like you said, take it for a ride, which I like that kind of metaphor.
Yeah, thank you. I appreciate that. And really, at the end of the day, we want to redefine how tissue-based diagnostics is done, and
Mhm.
the way and to scale it. And scaling it is not, we're so focused on the US and US markets. There's a whole world out there that I feel like this technology can just scale the pathology market for that. And I think about things such as remote consultation, but now start thinking of, maybe remote kind of pathology workflows, not just the consultation. So you start kind of thinking, okay, maybe there's something that can be done there, and just making the whole process again from chemistry to computation, from analog slides to digital intelligence.
Okay. That's very interesting. Yair, this has been a super fascinating conversation. I love talking about innovative technologies like this. I really appreciate your time coming on the podcast and talking about this stuff. So, Yair Rivenson, thank you so much.
Thank you, Dennis. It was a pleasure.
If you're looking for another episode of the People of Pathology podcast to check out after this one, here's a clip from my interview with Dr. Sofian Azded as we talk about how innovation in pathology might just be an ethical requirement.
It should be unacceptable when errors occur due to non-systematic flaws, like a simple label mix-up caused by a process we all know is vulnerable. We know the workflow isn't perfect, and most of people are doing their absolute best within that system. But the ethical issue arises when we know we are placing human beings in the critical roles, asking them to perform tasks all day long that the human brain is simply optimized, like a constant checking, etc. So if we recognize this vulnerability and both potentially know that better methods or technology exist or could be developed, and if we know that and yet we do nothing tangible to improve that weak point, that's where the ethical problem lies.
You can hear more from Dr. Sofian Azded in episode 204. All right, big thanks to Yair Rivenson. This is really fascinating stuff. It's rare that we see technology that doesn't just improve a process in pathology, but actually changes the foundation of how the work is done. And that's exactly what Pictor Labs is doing with virtual staining. As we mentioned, Yair didn't begin in pathology. He arrived there because he recognized an opportunity to solve a problem using the tools that he understood best: math, engineering, and computer vision. His work was the spark that eventually became Pictor Labs. While working in engineering, he saw firsthand how labor-intensive, slow, and destructive chemical staining can be. That insight led him to ask a bold question. If deep learning can enhance images and reconstruct missing information, could it learn to stain tissue as well? The answer turned out to be yes, and that yes became Pictor Labs. The implications of this technology are huge. There's less chemical waste, which is significant in immunohistochemistry. There are much faster turnaround times, a few minutes instead of several hours. There's less variability in staining. But most importantly, virtual staining means no tissue consumption. Now think about that. You could do as many stains as you want on a single tiny biopsy specimen, and there would still be tissue left for molecular studies. In this era of trying to do more with less, this could be revolutionary. One other exciting part is where Pictor Labs is heading. Yair talked about building a data layer for pathology, where tissue can be explored digitally, free from the constraints of glass, reagents, and irreversible processes. It's not just replacing chemistry with AI, it's expanding what pathology can be. As Pictor continues developing new stains and partnering with pharma, biorepositories, and research labs, it's clear that virtual staining isn't just a clever innovation, it's a glimpse into the next era of tissue-based diagnostics. Yair's story is a great reminder that the future of pathology is going to be shaped by people who bridge disciplines. Engineers, AI researchers, and pathologists working together. And this comes from innovators who look at long-standing processes and imagine something radically different. I hope this episode left you as inspired as I am. If you want to learn more about Pictor Labs and follow their work, all the links will be in the show notes. Don't forget you can follow this show at People of Path on both Instagram and Twitter, or just connect with me on LinkedIn. Thank you for continuing to share the show with others. Together, let's inspire the next generation of pathologists and laboratory professionals. This show is a member of Health Podcast Network. Thanks for listening. I'm Dennis Strank, and I'll talk to you next time on the People of Pathology podcast.